My talk for today is strictly connected to what Luca Casagrande presented before me. I will show you what the Gaia-ESO Survey CoRoT collaboration is. This collaboration is the result of a big effort made by the CoRoT RG community in order to show to the Milky Way archaeology community how powerful is the combination between asteroseismology and spectroscopy applied to a big sample of stars. The Gaia-ESO survey is a survey that aims to systematically cover all the major components of the Milky Way. It aims to provide a homogeneous overview in distribution of the kinematics and elemental abundances of the thin and thick disk, of the halo, of the bulge, of the open clusters, and it will offer to the scientific community a very homogeneous set of atmospheric parameters and radial velocity. And this target sample was done with a very well-defined selection criteria. The information of the history about our Milky Way is encoded in the stars, in the chemistry, in the velocity, and position and age of the stars of its components. Gaia-ESO survey will provide information about chemistry and velocity, while distances and ages are one of the major problems when handling with galactic archaeology. Talking about distances, for the moment we have a complete sample of precise distances up to 10%, confined to 100 kiloparsec, that is the sample of Hipparcos. This sample will be widely enlarged by the Gaia satellite that will provide distances with an error below 10% in a volume below of about 10 kiloparsecs. While waiting Gaia, we can use the CoRoT giant stars that can reach distances up to 10 kiloparsec, as is highlighted here in these two beams encoded in blue. As I said before, Gaia-ESO survey is a public spectroscopic survey. It will observe about 100,000 of stars, and it was designed as a spectroscopic support of the Gaia-ESO astrometric satellite. The PIs of the survey are Gary Gilmore and Sofia Randich, and to the survey, there are more than 400 co-investigators from about 90 institutes all across the ESO. The stars are observed by using the flame spectrograph located at ESO-VLT in Paranal. The observations are performed in parallel with two spectrographs, the UV spectrograph, that is a high-resolution spectrograph, and the giraffe spectrograph that works at lower resolution, about 20,000. These are the status of the survey in April 2014. So far, the Gaia-ESO survey observed for about 150 nights of the 500 nights that it obtained. The average signal-to-noise of the spectra is quite good. At low resolution, the spectra has a signal-to-noise ratio of about 70, and at high resolution, the signal-to-noise is about, the average signal-to-noise is about 80. The most important aims of the Gaia-ESO survey, as I said before, is to deliver an homogeneous set of atmospheric parameters that is the results of a synchronization of 90 nodes that perform the spectral analysis. There is also the creation of a benchmark catalog of stars published by Paola Joffre and collaborators in 2014. This benchmark catalog is very useful because it will be suitable for the Gaia mission, and it can be used also by other surveys that are ongoing or that are programmed in the future. Another aim is to investigate the major properties of the Milky Way. This has the metallicity gradients, as showed by Rachel Blanco and collaborators and Maria Bergeman in the latest Gaia-ESO Survey publication. And then one of the aims that are important for us is the integration of asteroseismology in the calibration process and in the use of the solar-like oscillation giants for investigating the Milky Way archaeology. So, the most important ingredients for investigating our galaxy are accurate element abundances, accurate ages, and accurate distances. So what can do solar-like oscillation giants with these problems? Also Luca Casagrande showed that solar-like oscillating giants can be really useful because they can provide accurate ages plus the evolutionary status. They can provide accurate distances, and also by using the seismic gravity, by fixing the gravity to the seismic one, it is possible to reduce the error on the element abundances determination. Nowadays, the solar-like oscillation giants are being implemented in the ongoing surveys, like, of course, Gaia-ESO Survey, Apogee, Hermes, and RAVE. Okay, distances, okay, probably you heard this 1,000 times during this meeting. Distances can be derived by combining the radius from asteroseismology plus the temperature derived from spectroscopy. The uncertainty reachable with this method goes from 10 to 15%, and with high-quality data, it's possible to obtain an error on distance of about 5%. First distance estimate has been done by Milio and collaborators in 2013, and we can see in this plot that the distances reached by solar-like oscillating giants can go up to 10 kiloparsec from the sun. Another information that we can have by combining the seismology with the spectroscopic information is the age. As a matter of fact, the age of red giants depends on the time that the star spends in the main sequence, and this depends on the mass and on metallicity of the stars. As we can see, by reducing the error on the mass and thanks to the information about the metallicity, it is possible to reduce the uncertainty on the age of red giant star up to 30%. And this error can be improved also when we know the information about the evolutionary status of the star. Another information that we can have thanks to asteroseismology is a precise and accurate value for gravity. And this seismic gravity is has a very weak dependence on temperature. A shift on temperature of about 200 kelvins leads to an error of gravity of only 0.02 dex, and the high precision can be achieved. By fixing the surface gravity to the seismic values, following my test, we can see that it's possible to increase the precision of the atmospheric parameters. As an example, by using the high-resolution spectra collected by Gaia-ESO Survey, it is possible to reduce the error on the temperature from 70 degrees to 40 degrees, and the error on metallicity from 0.1, about dex, to 0.05 dex. In conclusion, asteroseismology of solar-like oscillating giants is a really useful tool for surveys. It can provide improved ages and evolutionary status. It can give distances with an error of about 10%. It can provide a useful calibration sample for gravity, and it provides solar-like oscillation stars are a big sample. CoRoT and Kepler can provide about 2,000 red giant stars with ages spanning from 2 to 12 kiloparsec, so basically the age of our Milky Way galaxy, and distances spanning from solar neighborhood up to 10 kiloparsec. So in this view, the CoRoT Gaia-ESO Survey collaboration started. It started in 2013. The CoRoT giant group provided a sample of 1,400 red giants that present a solar-like oscillation. In addition, the CoRoT red giant group provided another additional photometrically selected giants for filling the fibers, as we can see later. The field of the stars belong to the LRC01 field, and the field is quite large. It is 1 per 2.5 degrees, while the instrumental field of view is only 25 arc minutes. This means that the solar-like oscillation are distributed very widely in the field, and for each pointing there were only 50 stars. That's why we added an additional sample of photometrically selected red giants for filling the fibers of the instrument. So we take care of the coverage of the CoRoT fields with the instrument, and so far, of the 34 fields that we prepared, 13 fields have been observed. 55 targets are being observed at high resolution with UVs, and more than 1,000 stars have been observed at low resolution. What we aim to do, and what we are doing now, is to derive more precise atmospheric parameters by fixing the gravity to the seismic value, and then to derive the elemental abundances. The iron abundances in particular, and alpha elements for giraffe stars, and for UVs we aim to obtain precise abundances of the alpha elements, S elements, and iron peak elements, and in addition lithium, sodium, and carbon when the signal-to-noise ratio is very high. This is the first temperature gravity distribution of the 1,200 stars of CoRoT red giants observed by the Gaia-ESO survey. These are the stars present in the data release 2. And as we can see, the diagram is really good. And in here, I highlighted the stars that has seismology. These are the stars for which we have delta nu and nu max. We are using these stars for calibration purposes and for testing the performances of the different pipelines. In here, I compared the seismic gravity with the gravity derived by Gaia-ESO survey with the gravity derived with the seismology. The agreement is quite good. The difference is only 0.2 dex. And this is really useful, as I said before, for testing how the homogenization is going, for testing the behavior of different pipelines, and for seeing if there is any shift of trends with the gravity following metallicity or temperature. Then what we really want to do is to start to investigate the properties of our Milky Way by using this sample of solar-like oscillating giants. And for doing that, for example, we can observe the distribution of the stars in the diagram of iron versus alpha elements. Alpha elements and iron are produced in 2 different time scales, while alpha elements are produced in a fast star-forming region. Iron is produced much slower. And this diagram is, in this diagram, we can see how metal pool stars are more alpha-enriched than metal-rich stars, and this is a very well-known result. In here, again, I highlighted the stars that have seismic information, and we can see again that the trend is confirmed, and also it is confirmed this gap at this level. And again, I wanted to check this distribution in mass. I calculated the mass of the stars from the scaling relation, and this is what I obtained. I obtained that the distribution of the solar-like oscillating giants in the LRC01 observed by Gaia-ESO survey followed the same distribution that obtained million collaborators in 2013. That is the same distribution simulated by the Trilegal tool. And the same result I got from the radius. Again, I derived the radius from the scaling relation. And again, the distribution of the radius of the sample of CoRoT stars in DR2 follows the simulation and what Milio and collaborators founded. And this is really important for for our investigation. We can see that the distribution is the same of what found in 2013. So this sample can be really representative and can be really useful for starting to investigate the properties of the disk. This, again, by using the radius calculated from seismology, I calculated the distances, and this is the distances distribution of the sample. And this is the spatial distribution in X, Z, and Y. And this is the distribution of the stars in radius, in galactic radius versus the iron abundances. And this is part of a project. All this work is part of a project that I am leading in the Gaia-ESO Survey. It is a project on galactic archaeology using the CoRoT red giants. And again, this is the distribution in metallicity of the solar-like oscillating CoRoT red giants. And what we aim to do is to investigate it, as Luca Casagrande explained before, details of the metallicity distribution. We are particularly interested in the metal-rich stars that probably are all metal-rich stars formed in the inner part of the disk that possess disk kinematics. And also we are interested in the metal-poor tail of the distribution that can be halo stars or a result of migration. So in conclusion, asteroseismology is a powerful tool for big surveys. It can help in deriving accurate ages, distances, and abundances. Nowadays, Gaia-ESO Survey is observing a sample of 2,000 CoRoT giants located in LRC01. The calibration and homogenization process is ongoing by using this sample as a calibration benchmark. We are taking part in project on galactic archaeology, and we are now deriving mass, radius, and ages not only by using the scaling relations, but also combining the information coming from metallicity, from spectroscopic metallicity. And in the future, there are some Gaia-ESO survey targets that are in the K2 fields of view, and we aim to introduce these stars in the target list. And that's it.
Very nice work. I was wondering, are you also going to do this for other fields in the CoRoT observed?
It's up to the PI. I think as long as we are obtaining very good results, I think that for sure the community is interested to introduce also the other fields in the Gaia-ESO survey. So I think so.
Yes, over there, Mark.
This is really, really beautiful work, and it's actually really nice to also have optical spectroscopy. In the case of Apogee, we have infrared spectroscopy, and we also saw a gravity offset with respect to seismology. Have you traced the origin of the gravity offset? In other words, is that a consequence of an identified issue with the spectroscopic gravities, or is it a mystery?
I didn't understand perfectly because the acoustic is quite poor, but I think, are you referring to this?
Yes, in other words, you have a 0.2 dex offset there.
Yeah.
And presumably that reflects your best atmospheric solution. And so my question is, what caused that? Do you know?
This is quite complicated because we are comparing gravities that are coming from a homogenization process that put together the results in gravity of different nodes that adopt different pipelines, that adopt different techniques. And this is something that we are going to do now. We plan to ask to each different node to compare their gravity to the seismic ones and to see what is happening.
We will thank again Marina. And this end.